magic stasis illusion?
What is that?
Even if we don't do them, can you post them later so we just go them?
Well, sure, but if you see what this is, it's actually.
Pretty blank? No.
Oh no, it happens. Oh, no, okay, there is something there. Yes. Oh, it happened.
It's a pretty low-tech way to bring that in.
Yeah.
Whoa.
Okay. I can post what I have. They're not necessarily complete lecture notes. It's definitely a weird.
That is so
Okay. Yeah. So basically, what these topics are so we know what the surface code is. So the stuff that I haven't talked about for the surface code is how to do computations on the surface code, and how do we do the error correction itself. What do you do to correct the errors? What's the decoding algorithm that you use? Right. For quantum chemistry is interesting because this is it's a kind of a quantum algorithm, and it's interesting for me, I think, because it's sort of the kind of quantum algorithm that we run on near-term quantum devices. So for Shor's algorithm, you need thousands of qubits, which we're not, with very low error rates, which we're not getting to anytime soon. But for some of these quantum chemistry experiments, you could possibly break the state of the art for classical computers with just hundreds or 50 to 100 to 200 qubits.
That seems pretty exciting.
So that's interesting too. Now I think it's interesting because some of the techniques used for quantum chemistry are used in other algorithms as well. So it's not necessarily physical algorithms; they're used in other mathematical algorithms. Quantum query complexity. So this is a classic topic. It's like when we were talking about Grover's search algorithm. So Grover's search algorithm is you have a function which and you have a string. You can query the bits of the string one at a time, but in superposition. And the question is, how many queries do you need in order to find a one if there's one? And we proved that you can do it using squared event queries, order squared event queries quantumly. In fact, that's tight. And so quantum query complexity is how we show that's tight. How you show that you need squared event for that problem. And more generally, how do we understand lots of other kinds of query problems? And so query complexity it's a very nice field that's pretty well understood now quantumly. So it's actually interesting because quantum query complexity is much better understood than classical query complexity right now.
It's really weird.
And it turns out a lot of the lower bounds are tight. So actually we can derive quantum algorithms using the lower bounds. So it's an interesting field. Anyons are, I don't know what's the way of saying this. It's a sort of a generalization of qubits maybe. So it's a different kind of physical system. Well, it's conjectured to exist in different kinds of physical systems, but it's a very nice mathematical model that you could say generalizes qubits or something. And it's of interest not just because it's mathematically nice, but also because it's these kinds of systems, if they exist, they're conjectured to be sort of inherently fault tolerant. So the noise rates would be much lower than in current devices.
Is that part of what like Microsoft is searching for, or are they trying to build?
Yeah. Yeah. So Microsoft's system is based on a very simple NEI model, which they conjecture exists, which they hope is low noise rates. Yeah. Yes. So this is not about the implementation. This is more about the math. I'll just quit and start it again.
It's been picked for you.
So what would you like?
Do anything. Chemistry sounds exciting to me, but
I think that this and the chemistry are the most exciting ones.
here's more.
Yeah, I feel like those are the two best ones.
Okay.